All right, hello everybody. Today I'm going to help us to understand more about the magnetic vector potential. I'm hoping that today we're going to see the whole thing kind of come together. And so please bear with me. This is the first time that I've actually done a a complete video lecture. Um, I'm starting right now at 5 p.m. my time, so I'll try to finish on time. And so the basic thing that I want to do is I'm going to review our work on boundary conditions that we did last time we met. And this will also help get us ready for our exam on Friday. And take a look, also extend that to how do we talk about boundary conditions on A, the magnetic vector potential. Then I'm going to begin to talk about A for dipoles. And I'm going to go through a little bit of derivation, and I'm going to try to make sure that we come back and we really get the point about what this is all about. And then lastly, I'm going to make some parallels with the magnetic dipoles as is connected to the electric dipoles that you've seen before in electrostatics. So I'll just call this as the magnetic dipole moment. Okay, so all right, so here we go. So so the all of these things you can find also on the notes that are online, and I'll also scan these and upload them onto our shared drive as soon as I'm done here. So and toward the end also I will be giving some hints and an overview of the homework, which will be due on Thursday evening. Okay, so last time we actually used a tutorial to actually get some insight about, let's see here, my microphone is kind of, let's see here, if I can just kind of, there we go, okay. So we got some insight about the boundary conditions on B. So basically, to just summarize, we saw that B above minus B below some interface was equal to basically mu naught times K absolute value in the K crossed in hat direction. So what does that kind of really mean here is that if I've got my interface here, and let's say that I had K's going kind of into the page here, then if you remember, we had some B above, which could be broken into a component that was parallel to the surface and perpendicular to the surface, and then some B below, which had a perpendicular to the surface and parallel to the surface. And what we had said there basically was that because B dot dA was equal to 0, in other words, if we looked at the divergence theorem, and we saw that the triple integral of the divergence of B d tau, we know that this here was equal to 0, and that allowed us to add up the B dot dA for all of our surfaces. So just to kind of remind ourselves that we have our A's kind of point in all of these different directions, and we did basically a B times A for all those things. And we mathematically said, well, you know, these sides, they're going to be really, really small because I'm shrinking them, right? So I'm just kind of going over that argument that we used for last time here. So our delta Z became very, very small. And one of the things that came out of it was that B times delta A above in the C hat direction plus B below dotted with delta A in the minus C hat direction, that equaled to 0. Okay, and so then from that we saw that the above component perpendicular was equal to the below component perpendicular. So okay, so then that's B above perpendicular and B below perpendicular, that these are actually, how do you say, these are continuous across the boundary. And then we also worked a similar thing where we made a loop that went around, and again we basically said, oh, it looks like that this and this are going to be the only ones that actually contribute. And so again we worked that integral of B dot dl equals to B above parallel times some length of this loop here. Oops, some length of this loop. And then we said, okay, minus B below parallel times the length of this loop has equaled to 0. And again, how do we know? Sorry, I misspoke there. Not 0. It's equal to mu naught times the current enclosed, right? So B dot dl is mu naught times I enclosed, which if you have a K here, then if you remember, K is just defined as a current per length perpendicular, so something like this, right? So in this case, if it's just a constant K, then I can write this as mu naught K times L, and that will actually give me my current enclosed. It's just K times L in this case. So the L is the perpendicular to the direction of the current. So in other words, basically I got then two conditions, namely that B above parallel minus B below parallel equals to mu naught K, where the L's are all canceling out here. And I think that's about it. Oh, and actually there's an overall minus sign here because of the convention that I chose here. So, okay. So anyway, so that's just kind of a review of what we did last time. That's from the tutorial. That is something that will be on the exam. So I just want to make sure that that's clear. How do we get those kinds of boundary conditions? Now, also, what about A? So A, the magnetic vector potential, or the voltage, as some like to call it, is, if you think about this, actually, you could say, if we had some kind of boundary, we were wondering what the boundary conditions on an A were, so here's kind of my below and here's my above, I could make a, let's see here, I could make a Gaussian pill box like before, but I actually know something, that the divergence of A is equal to 0. Well, actually, if we looked above, the divergence of B was also equal to 0, and that told us that the perpendicular components were continuous. So I want you to be able to go through that same argument to know that A above perpendicular is equal to A below perpendicular. Okay, and you can go through exactly the same argument of adding up the contributions to each of those sides in a Gaussian pillbox. So I want for you to be able to add up all the different components, for example, of A dot dA. There's going to be 6 sides, right? And so each of those is going to have some contribution, and I want you to be able to add those up and to get some practice with that. So another thing that I could do is I could actually make a loop here. So for example, I could say that there's an A above parallel going in this direction here. So I could say, okay, well, I'm going to do an A dot dl, right? And actually, if I think about that, well, A dot dl is essentially the same thing as the curl of B dotted with dl, right? And if you think about that, well, actually, we know this before, that we can use Stokes' theorem, that this is actually the same thing as B dot dA, right? So Stokes' theorem and divergence theorem are coming in to be very, very handy for all these types of relationships. And if I look at this here, I can say, oh, okay, that's just the magnetic flux. So in other words, the magnetic flux is essentially determining this, the flux through this loop here is essentially determining what my boundary conditions on A are. So in other words, if I go around this loop here, I could again make a delta Z like I did before. I could shrink it down to 0. So then I could basically say that A above parallel times L minus A below parallel times L is going to be equal to the magnetic flux. And if I make this Z, delta Z, really, really small, well, then I can, oh, I'm sorry, there's nobody to tell me move it up. So if I have my magnetic flux, and if I make this delta Z really, really small, well, then as long as this magnetic flux is finite. In other words, that I don't have any like delta functions of B, which I don't know. At the moment, I can't really imagine a physical scenario where I have a delta function of B, but maybe it could happen. And so here we would have that this is equal to 0. So in other words, this is telling me that A above parallel is equal to A below parallel. In other words, basically, what I'm seeing here is that that I have the perpendicular components and the parallel components are all continuous. So in other words, A is always continuous, just like continuous, just like the electrostatic potential is. So maybe this would be a good point here to then kind of review again our triangle, so that in Griffiths we saw this triangle between E and V. So we saw these kinds of things here, and this was basically the same as looking at a J, a B, and an A. Okay, and so in other words, if we were given, and I'm going to make sure that I highlight that which ones are vectors. So this is the only one that's a vector here, actually. And so these pictures are very similar, and I passed out a sheet, and as well as I posted online these two triangles. So actually, you know what? I didn't post it online, but you can find those in the book. These are just two figures that you'll find in Chapter 5 and I believe Chapter 3. But basically, if you wanted to figure out what B is, and you were given J, then you can use Biot-Savart law, right? If you had B and you wanted to figure out J, well, you could just take the curl of that B, and that would give you a J in that region. If you have A and you want B, that's super easy, right? You just take the curl of A and you get B. If you have B, can you compute A? You can, and that is actually one of the homeworks from last week, was to compute that, and the solutions are posted online. And then lastly, if you have A, can you compute J? Yeah, no problem. Again, we chose the Coulomb gauge, in which it looks very much like the Coulomb potential here, and we can use the Laplacian equation. And then again, we can also go the other direction here, where J times d tau prime over script r, and we're doing a triple integral, and we can add up all of those J's, and we can get our A. So in other words, that kind of follows from the solution basically of this Laplace's equation. So the boundary conditions on A and B, those are going to be very important in the next chapter when we're going to be considering magnetic fields in matter. And so we're going to kind of work in analogy to some of the work that we did before when we looked at electrostatics, and we similarly had boundary conditions on the electric field and boundary conditions on the potential. Okay, so that concludes our discussion about boundary conditions. I'm now moving on to talk about this magnetic dipole stuff. So remember, we've done some stuff already with, we've actually talked about dipoles, whether you realize that we have or not. If you imagine a loop here, I'll give it some radius r at the moment, and if you think about this, if it has some current going around in a circle, then I can use a right-hand rule everywhere along this thing, and I can see that there's actually some magnetic field going up through this thing here, right? So B's kind of, I just want to say that B basically points out and kind of around. And, you know, if you kind of looked at it, you might be thinking, well, wait a second, this kind of actually looks like an electric dipole. And actually, you'll see that there really is a very solid connection between these. This is a very kind of a familiar pattern, right? It looks very much like if I had a plus Q and a minus Q, the electric field that kind of we would see kind of around these guys. I'll just draw it few lines here just so you can kind of remember. That was a really crappy dipole, but I think you get the point that there's kind of this picture like this, right? That it kind of goes out, and gosh, it kind of looks like the same thing for these magnetic dipoles. It looks like it might be exactly identical. So we figured out how to calculate B. Remember, we used Biot-Savart, right? And that was fine, but it was a little bit of a pain to calculate B, the magnetic field strength. But this is a really important type of field, and hopefully by the end of this discussion here, I'm going to convince you why this is a really important thing. So in other words, what I want to do is I want to consider calculating the A for this thing, basically using this addition here, basically like this. And if you look, I'm just going to refer you to in Griffiths, basically equation 5.66. He discusses that A could also be written, for example, as mu naught I over 4 pi times the integral of 1 over r dl, okay? dl prime, right? So we're adding up all the little pieces of current, right? And that's actually the same thing as this thing here, because it's basically just the idea that my J now has a couple delta functions in it, so it's reducing the dimensionality of my integral. There's another similar one for K's and dA's if you'd like, but this is the one we're going to be working with here. So I'm trying to compute A for a loop of current. Okay, sounds like a kind of a, how do you say, straightforward enough of a problem. Nothing can go wrong here. Well, there's a little bit of mathematical pains, and if you look in Griffiths, you probably have been reading through section 5.4.3 in Griffiths, talking about the multipole expansion. Okay, and I'm going to help walk you through that here, and hopefully we can see what the value is in going through this kind of exercise. So basically, I'm interested in computing this A here, right? This vector A, and so we can think about this actually in a way that we did before. Is that this script R? If I want to think about a loop here, if I had a piece of current, so a dl prime, and this is the center, maybe, let's say, and I'm interested in calculating the potential out here at some vector r from the center of this thing, then this would be my r prime. If you can read my handwriting here, r prime is going to point to this little piece of current, and then my script r, right, is going to connect the two. This is going to be r minus r prime, just like we did before, right? So, okay, that's kind of interesting. So, so in other words, script r, you could say, as a magnitude of this vector, could be equal to, basically, I'm just going to subtract these, and I'm going to dot it into itself, and so that would give me r squared plus r prime squared minus 2r r prime times the cosine of the angle between them. And I'll call this angle theta prime, and that'll be the angle here. I'll call this here theta prime. And I'll take that to the 1/2 to make it an actual magnitude here. Now, it turns out that if we are, now this, and also I want to mention that this is not like theta, our usual polar angle. This is the angle between this vector and this vector here. Okay, so basically, I'm going to hide a little bit of the math here so that we can get to the point in a reasonable amount of time. That if r is much greater than r prime, in other words, is a really tiny dipole, then script r is basically equal to 1 minus, I'm going to just write it here, Okay. So what I've done here is I've basically expanded, or I can say that 1 over r is equal to plus the higher order terms. Okay. So Griffiths actually points out that this here is actually the Legendre polynomial. It's not just a coincidence that, that this looks remarkably similar to our multipole expansion that we did for electrostatics. Okay, so I'm going to continue on with this idea here, so that basically if I'm adding up, in other words, I'm trying to add a at r equals to mu naught I over 4 pi times the integral of these dl prime over script r, that I can write it as instead mu naught I over 4 pi times first just the integral of oh, and I'm going to bring out my r here, right? So this r is not a part of the r prime integral, right? So I'm going to just be integrating over my dl primes, right? A closed loop. And then I'm going to add that to r prime cosine of theta prime dl prime divided by r. And I'm putting it in this sort of suggestive way here that it's trying to kind of make it look reminiscent of the multi-expansion of what we did for V. But actually, if you notice this thing here, you might be thinking, if you just look at it without the vector, you might be like, oh, we're going around a circle, and it's integral of dl, so that should be 2 pi r, right? 2 pi r, where r is the radius of the circle, right? Well, the catch is that this actually leads to 0 because you're adding up a bunch of vectors that go around in a circle, and when you finish going around a circle, you're back to where you started. So this is our actual monopole term, and this is equal to 0. This is actually we call as our dipole term, okay? And this is what we're really interested in here. So the monopole term goes to 0. Each successive term, if we were to continue to include this like r prime squared terms and so on, is that we would get an extra 1 over r each time we went to the next order here. So in other words, basically to first order, a of r is approximately equal to mu naught I over 4 pi r squared, and this is going to be the integral of r prime cosine theta prime times dl prime. Okay, so alright, so now we're left with something that we could actually compute in principle. Notice how actually there is an r prime that's actually kind of hidden into this cosine of theta prime, which is why we can't really take it out of this integral thing. But actually it's going to be a total pain to try and compute this. So we're going to play around with some tricks here. One of them is that r prime times the cosine of theta prime, if you refer back to my picture earlier, that's actually equal to r prime dotted with just the regular r. So in other words, that was that r prime, this was my r, and if you take the dot product of the two, there's your theta prime, right? So that actually you could kind of rewrite that thing. The other thing to notice is that r prime dotted with r hat dl prime, okay, that's kind of what we have now, is equal to minus r hat crossed with the double integral of dA. Now, this is not an obvious thing at all, okay? In fact, you need to use Stokes' theorem and a couple of identities, and I'm going to skip this for right now because it's a kind of a, oops, I had not moved up the sheet. So now there you go. You can see what I was actually writing a moment ago. So you can see that this is you know, definitely an issue here, is that if this is a difficult thing to compute, and so basically, I guess I'm asking at this point that you take kind of a leap of faith with me here on this derivation, because it can be a little bit dizzying to see all these things. But if you defined your magnetic moment as equal to your current times the integral over your area of your loop, we're going to call this as the magnetic moment of the current loop. Okay, and hopefully you'll appreciate why in just a moment. Why are we defining this quantity here? So in other words, we have a situation here where, okay, so then that means that, like, for a flat loop, for example, so if I just had a loop here, remember that the normal to this area here would be pointed straight up out of the loop, right? So this is kind of my surface here. And if I have some current I going around this thing here, and let's say that I have some radius A, then the integral of dA prime is just going to be equal to the area, which I guess I would write here as pi a squared, in the in-hat direction. Okay, so that's just for like a flat circular loop. And keep in mind also that you know, for a loop, how would you know whether it was pointed straight up or straight down? Use the right-hand rule. And so, like, that right-hand rule sense of in-hat is basically whatever line integral you're doing kind of around, then your thumb is kind of pointed up. So okay, so then finally, putting this all together here then, so this is just like kind of as an example here of what this would kind of look like in practice. My A now is, again, this is an approximation, approximately equal to mu naught I over 4 pi r squared. And then I have this integral of dA crossed with r and dA prime, and I'm crossing that with r hat, and as I have up here. In other words, if you flip the sign, then if you flip the ordering, you just flip the sign, and then I can recognize, oh yeah, that's the thing I defined as this m, right? So that's equal to mu naught over 4 pi r squared times m crossed with r. Oh, so many of you have been asking me, like, what is the meaning of this A, and how do I think about it, and what does it physically mean? You've seen basically this kind of thing before. In fact, let's actually flip back to chapter 3. Should have earmarked it. With a multipole expansion. Yeah, here we go. So in chapter 3, we were doing multipole expansion, and we ended up getting, look at this. This equation that I just got here, and the equation for the electric dipole moment, that's really remarkably similar. We have a 1 over r squared dependence, p dot r hat, right, where r hat points from the dipole to the point I'm interested in. The only difference here is that it's an m crossed with r hat, which might not be too surprising, because if you remember, we have a lot of situations where a dot product kind of becomes a cross product in the magnetostatics world. So this is really interesting. The potential of a dipole drops off like 1 over r squared. The potential of a magnetic dipole also drops off like 1 over r squared. So we're getting somewhere. We can interpret A as the potential, basically, you could think of it as is kind of like the energy per dipole. So in other words, kind of like it's in analogy to this idea that if you had, I don't know exactly how to, maybe I was going to try to make some exact analogy, but I think that maybe you can see where we're going here with this. Okay, so let's see here. Let's kind of put this into practice then. If you had a little dipole that has some m, okay, and be careful with this m here, because in some of the homework problems we're also going to have the m for mass, which is unfortunate. We'll just make sure to be careful about what we mean by those so we don't get confused. and if here's my point R that I'm interested in over here, and this is the angle between them, then A would be equal to mu naught m over 4 pi r squared times the sine of the angle between them. And then I guess in this case, since m seems to point in the z hat direction, so m equals to m in the z hat direction, this would be z hat crossed with r hat. So actually, if this is in a kind of a spherical coordinate system here, where this theta really is the polar angle, then z hat crowded with r hat, well, what's that? Oh, that's the phi hat direction, right? So actually, then we could say that A points in the phi hat direction, just like the current itself, and that's something that we're familiar with. We've seen that before, that if the current is going around in a loop like this, then the A's are also going around in a loop like this as well. The A points in the phi hat direction. And then if you compute B, which I want you to do, and you will do for the in the homework, you'll take the curl of this A, basically, that we have here for certain situations, and you'll see that this looks just like the electromagnetic, the electric dipole. So okay. So I think that basically is most of what I want to say at this point, and now we'll begin to start talking about kind of some things that might be helpful for the homework. So if you, I'm going to start a new page here just because it's going to be a little easier. If I had a bunch of magnetic dipole moments, I could say that I could talk about the m kind of per unit volume, and I could call this as a capital M, which is we call as the magnetization. Okay, and that M is going to come up a lot when we talk about magnetic fields in materials. This is a lot like when we had the electric dipole moment, P per volume, right? Per volume, and that was what we called capital P. Remember, we put that little thing down here to distinguish between lowercase p and uppercase p, and this was called the polarization, right, of a material, right? So it's telling us how much all of these little dipoles are lined up with each other. So okay, that's kind of interesting, and that'll be something that'll be useful when you're estimating the strength of interaction between some toy magnets. There's a lot of analogies here. So one of them that you might remember is that if you had in the electrostatics case, if I had a dipole moment P pointed from the minus to the plus, and it was in the presence of a electric field E, then you could calculate the torque on the dipole, right? This is like, I guess we could say this is an electric dipole, that was equal to P crossed with E. Okay. Similarly, if I have a little loop here, and the M is pointed up here like this, in other words, that it's a little current loop like this, and it's in the presence of a magnetic field B, the torque on this dipole is equal to M cross B. Amazing parallels, right? This is something that's easy to show, and if you, for example, calculate the force on every part of this loop here, then you can use force is equal to I dl cross B, and you can integrate over this, I'll do dl prime here, and that is the same thing as, let's see here, for example, you're going to be needing this for the homework, so I'll just kind of point you to the right direction. So I think you know where to find this, but it's the beginning of chapter 5. This looks like it's equation 5.16 in my third edition of Griffiths here. So okay, that's kind of interesting. So we could compute this, and one of the homework problems is that actually we have a loop of current, and it's basically what I want for you to do is to compute the force like explicitly on each of these things. So I put it in the XY direction like this, so that when I did actually take this thing here and I flipped it up like this, then I would have kind of the more familiar situation of x, y, and so you could do something like this. Or what I've asked for you to do is to write the z, y direction here, where this and this will actually show up as something going into the page and coming out of the page. And then we're going to have our magnetic field, which I gave as equal to something in the z-hat direction plus something in the y-hat direction. So you draw your magnetic field, and you would compute the force on each of these things, and then calculate the torque. And I would use the symmetry of the problem as a guide here. That you'd probably compute the torque about some line that goes through the origin. So it might be, for example, if this loop is going to be rotating like this, then I would pick the x-axis to be the thing that I'm rotating about. If instead it's going to rotate like this, then I would choose the y-axis as my how do you say, axis of rotation, basically. So so in other words, like if I had two lines of current here, and let's say that I had a current going into the page here and a current coming out of the page here, then if this is my kind of my square loop and I'm looking at it from the side, then I can see that it has a magnetic field, a magnetic dipole M, and let's say that I had a B field that was pointed straight up in this case here, B. Then if it has an angle between them, theta, then I can say that the force on this guy here should be equal to I dl cross B. So dl crossed with B, it looks like the force here points in this direction, and it looks like this force here is going to point in this direction. So I can say force is equal to I L B, and then if I wanted to compute torque, that's going to be equal to R crossed F. And so R crossed F you could also write as, if you get your sign convention right, you could just say if this is my force on this wire here, I could look at it and say, well, I want the sine of the angle between the vector that connects between here and here and F. So that's this vector here and this vector here. So that's this angle. So, oh, that's the same angle as this angle here. So you could say it's equal to, if this is a loop that has length A and length A, right, so it's a square loop, then this looks like this is going to be A over 2, right, is my length here, times my force, which I can calculate as ILB, times the sine of the angle between them. So that's be one way to compute this here. Or what I've asked for you to do in the homework is to directly compute these cross products, remembering that if you had like an x hat crossed with a y hat, that would give you z hat, and that these things also permute. So I could do yzx and zxy, where I'm shifting them down each time. So maybe this will be helpful for you to have this kind of guide in mind. And anytime that you flip, a multiplication, that's going to put an overall minus sign on things. And you can always practice this by breaking them out into their components. But I think that you'll be able to figure this out pretty well. So in other words, if you compute the torque on this one and the torque on this one, then you'll end up getting something that looks like, well, I have the A over 2 times the force sine theta, and then I'm going to say the total torque is going to actually be twice that much. So I'll take away my factor of 2 here, and the force is going to be equal to ILB in this case, and so this is so that's going to be IAB in our case. So I end up having an A squared with an I, B times the sine of theta. Okay, cool. So we're actually getting something that looks like MB sine theta. MB sine theta is what we had up here. So that's good. That's good. We're getting getting something that's a practical result. Okay. So we've got approximately 10 minutes remaining here. I would probably pause at this point to ask about questions and see what you're thinking about things. I'm most happy to take questions, and if you're watching this and you want to shoot me an email, I'll try to respond as soon as I can. And I guess lastly, I need one more piece of paper here. Let's see here. I will talk about next that another analogy with electrostatics is that the electrical force is equal to the gradient of P dot E. And I think we just talked about this briefly. We talked about the forces, and that if there was an inhomogeneous electric field, that there would be an overall force on the dipole. And here you could also say that there's a magnetic force that has this exactly the same kind of setup here. So here's the way that we would write the force. So in other words, the magnetic dipole is actually going to get sucked into a region of stronger B field. And that is if the magnetic dipole is already pointing kind of aligned with the B field. So in other words, maybe it's been lined up by the torque. So you saw that there's a torque. That torque is going to always align, just to go back to this picture here, we're going to align this dipole until M is pointed in the same direction as B, basically. At that point, there will be no torque. So you can imagine if we let this situation go, you can see here that the force is pointed out this way, so you can actually imagine that there's going to be a torque pushing it this way, and then once it goes the other way, it would be going back and forth like this, right? So if it gave you, maybe if we wanted to do some crazy classical mechanics problem, we could actually ask for the oscillation period if we gave you the moment of inertia of something like this, right? So that's something to kind of consider or think about. But okay, so let's talk some practicals here. We want to compute some stuff for the homework. So let's see here. So we talked about the first one. The second part here is talking about a coordinate-free formula here. So, by the way, the homework is due on Thursday, on the 23rd. I wanted to give you an extra day here. So, coordinate-free formula, I think that I've given you everything that you need to know for this part here. Just use your vector relationships. Let's see here, and if you need some more hints, or if you want to talk about things, I will be available for the rest of this week, also Tuesday, Wednesday, Thursday. Okay, so this one's a really interesting question here, this thing about the donut. So I just wanted to remind you that I think it was back from January 25th notes. We talked about how to compute the current for the situation, basically, and so I think that you can use this to compute the magnetic dipole moment of this thing, and then you're going to actually take a look at a sphere, which would be a contribution of a bunch of these things. And so I guess the question that I'll have for you is does it really matter? The radius of this magnetic dipole moment when you're thinking about the gyromagnetic ratio. So remember that the gyromagnetic ratio is the ratio of the M, not the mass. It's easy to get confused. I know there's two M's kind of running around here, so we'll try to keep them separated. But the magnetic dipole moment divided by the angular momentum. If you remember, L is equal to R crossed with P, right? So that's the definition of the angular momentum, and so which for just like a point particle that's going around in a circle, we could say it's its mass times the radius. Let's say I'm sorry. Let me back up here. I'll say it's radius crossed with its momentum, which is mv, and if its momentum is always pointed perpendicular to its r vector, which it is in this case for a circle, then it'd be rmv times the sine of 90 degrees, right, which would be 1. So this is equal to the radius of this how do you say, moving around in a circle, times the mass. Okay, let's do capital M just to be really careful here about that, not the magnetic dipole moment, times its speed. Okay, so this is good, and we could even rewrite v, for example, in terms of omega and r, right? The way I always remember this is I say that the circumference is equal to 2 pi r, and then that reminds me that this is saying that the s is equal to theta times r, and then I could take successive derivatives of this relationship in the box here, and that will give me v equals to omega r, or a is equal to alpha r. That's a nice little trick to know, because if you're like me and you forget things often, you need to go back somewhere where you know that you'll be able to understand what's going on. So this is really cool. We're going to then use this information here to deduce the electron's magnetic dipole moment, and I really like this this question. I think it's a fun one. It kind of helps us to make everything kind of physical and intuitive, and there's a little bit of history here to kind of help you to sort of see what's going on. There is going to be when you compute it, you're going to be bummed maybe a little bit that it's off by exactly a factor of 2. In other words, I think that you should get a number that looks something like 4.6 times 10 to the minus 24 amps times meters squared is going to be the m that you get, right? So in other words, remember, this is meters. This is the magnetic dipole moment that you're going to find for the electron. And so you'll get that, and you'll think, oh, okay, well, and then you look it up online, right? And you look at it and you go, oh, I'm off by a factor of 2. If you put that factor of 2 in there, and you get something like 9.2 times 10 to the minus 24, and of course you can add more digits, of course, because you know some of these fundamental constants like the charge of the electron and h bar and the mass of the electron. You're going to find some really crazy, amazing agreement. And I hope this impresses you. I hope this is something you're like, wow, a classical model of an electron just spinning around in a tiny circle. And remember also, doesn't depend on the radius. This is another kind of weird and interesting thing about nature here. This is the gyromagnetic ratio, right, of a spinning electron. So, which allows us to then connect the dipole moment, magnetic dipole moment, to these fundamental constants. And so that's kind of a very interesting, sort of connection with some real physics. So I hope that you enjoy that. And it looks like we're just about out of time here. Lastly, I'm going to talk about the force between magnets here. That's our fourth homework problem here. And so you've hopefully already read through this here, and you've seen that you have two magnetic dipole moments. They're spaced a bit from each other. So you can either start with the coordinate-free version, or you can think about, or you can use the equation that's in Griffiths, talking about the force that the magnetic field of a dipole. So, for example, if you remember, magnetic field of a dipole in Griffiths as a function of r. That's equation 5.88. And if you just draw your picture here, you'll find that this thing's producing, let's say you could say M2 is producing some magnetic field, right? And M1 is in the magnetic field, right? So you might say, okay, well, I guess I could probably then figure out the force on this thing based on using this equation here. So I have, for example, I'm going to compute B from the second dipole, and then I'm going to evaluate it at the first dipole and dot it into M, and then I'm going to take the gradient. So you should end up getting something that's like a 1 over r to the 4th dependence. And the next thing that you'll do that's pretty cool is to then try applying this to a magnet, like a toy magnet, where you're going to have to look up the mass density and the atomic mass of iron, right? And so, for example, in my estimate, when I worked this problem, I just basically said, well, the density of iron is given to be about 8 grams per cubic centimeter. So I said, well, why don't I just say that it's 1 cubic centimeter? So in other words, it's about 8 grams, right? And remember, this is an estimate, right? So you're not going to need to carry on a bunch of significant digits. I want to not have this thing show up. Okay. So let's see here. What else? So you're going to compute that. basically what I want you to do is to have an experience here of remembering back to a free body diagram. So here's my south pole facing a south pole, and it looks like that if two dipoles are aligned in the same direction, it's an attractive force, right? That's like a north is touching a south pole. But if a south and a south are touching, there's going to be a force on this guy here, a magnetic force. But then there's going to be also the force that the Earth has on this magnet, which is a gravitational attraction, right? And when those balance each other, right, in this free body diagram here, then you're going to have a situation where you can solve for this distance that these things are apart. So this h, I guess you could call it here. So, all right. So I think have fun with that. Ask me questions. Work with each other. I think that. It's really good to get practical about these things, especially when as challenging as a derivation it was to figure out this magnetic vector potential. That's not where I want you to be focusing your effort, but rather on the results and kind of what is this magnetic dipole moment and what are its properties. And hopefully now you've been able to see that this magnetic vector potential has some meaning as being the energy per dipole moment. I think that's it for right now. And where we'll be heading from here is we're going to take Wednesday to do some review, and I'll be answering questions that you might have, and help get you ready for the exam on this upcoming Friday on February 20 what is that 4th, and so some of the topics that we will do is we will have some continuation of a bit of Ampere's law. We'll be looking at the magnetic vector potential. We will be looking at boundary conditions. And let's see, I'm trying to think if there's something else. Probably would be good if we made a sheet together of the topics. But I'm hoping that by now you're starting to get very comfortable with doing these manipulations, especially with the divergence theorem and Stokes theorem, and that you can work through these things, and that also you can see the connections between the electric fields and magnetic fields, in terms of looking at the parallels of what we made, as well as the parallels between B to A is the same thing, or sorry, B to J is the same thing like A to B, and I think you've seen that before. For example, in February 8th, we made some more discussion about that. Okay, thank you very much for watching this video, and please leave me any comments, even if it's like something silly like the volume's not loud enough, and I'll try to respond to those kinds of things. Hope you have a good week. Thank you for watching.